And final spacecraft preliminary design review. And this is the first ever collaboration between the astronautics track of aerospace engineering and robotics track of mechanical engineering. We're currently this team, that long Latin name, is working with Sparta Robotics, which is being mentored by Dr. Jacopo Gentilini. And at this time I'll pass it to Catherine Naya, who will project manager.
Thank you, Dr. B. Hello, everyone. My name is Catherine Ayot. I'm the project manager for Coeus Promethia Genna. Thank you all so much for being here today. We're very excited to see so many people here. Today we'll be going over the preliminary design review for Project Gemini. At this time, I'd like to introduce Nina Rogerson, our assistant project manager for Coeus Promethia Genna. Looking at an overview of what we'll be discussing today, I'll be starting with an introduction to both the mission concept and the system of systems overview and concept of operations, followed by the system of systems definition, and each system's definition and validation. This will be followed by the overall system of systems validation and conclusions in programmatics. Looking at the mission concept overview, Project Gemini is designed to be the emulated planar environment for satellite refueling mission, meaning this is a simulation of an in-orbit satellite refueling maneuver. In order to achieve this goal, our team, Coeus Promethia Genna, has developed 3 systems: a chase vehicle system, a target vehicle system known as Castor and Pollux, the twin constellation, and a visual tracking system to determine the positions and orientations of both of the vehicles during the mission. We are also interfacing with Sparta Robotics for the development of a capture system in the form of a robotic manipulator, which will actually perform the maneuvering between the 2 vehicles. We'll be going into a brief concept of operations to understand how this very complex mission works. At the beginning of our mission, all of the electronics will start up and the chase vehicle system will begin hovering using an air bearings mechanism to achieve a frictionless environment. The visual tracking system will be using an onboard camera and object identification to determine the positions and orientations of both the target and chase vehicle systems. During the approach phase, the chase vehicle system will use the coordinate data from the target vehicle and propel itself using compressed air to the target vehicle, at which time it will perform a station-keeping maneuver in order to maintain its position using a deadband controller on board. During the docking phase, the robotic manipulator will use its own camera to look for the capture point on the target vehicle, which it will reach out and grab and actually pull the 2 vehicles together to dock, using electromagnets to maintain that connection. For the refueling, we'll be refueling in a capacitive circuit using a refueling mechanism on the robotic manipulator, charging a capacitive circuit and lighting an LED to constitute refueling. In the undocking mission phase, the robotic manipulator will reorient itself on top of the chase vehicle, as it is right now on our model here, just sitting on top. And at that point, the chase vehicle system will return to its initial starting position, constituting the completion of the mission. Here's our design team layout. We have 3 different main teams: the visual tracking system, the chase vehicle system, and the target vehicle system, as well as an integration team to make sure all the systems are able to work together, all of whom will be introduced to you during this presentation today. At this time, I'd like to hand it over to Nina Rogerson to go over the system of systems.
Thank you, Catherine. Hi, everyone. I'm Nina Rogerson, and I will be going over the system of systems. First, I would like to introduce my fellow integration members. We have Noor Rashid, Seven Reinhardt. Oops. As you can see here, we have the design tree for our system of systems. As Catherine said, we have a chase vehicle system, a target vehicle system, a visual tracking system, and a robotic manipulator. I will be going over how all these systems interface and work together. First, we have the visual tracking system. The visual tracking system will be docked to the ceiling of the lab we are testing in throughout the mission and will watch both vehicles throughout the mission. It will also relay the position and orientation of both the vehicles to the chase vehicle so that it knows itself and the target vehicle's position throughout the mission. It does this by having its onboard camera, the Raspberry Pi, and the Bluetooth to do this communication. Next, we have the target vehicle system, also known as Pollux. Pollux's process is to remain still throughout the entire mission and to support the refueling receptacle. It does this by having visual tracking nodes on top, so that the visual tracking system knows where it is at all times, It has a refueling receptacle right in the middle, so the robotic manipulator can actually perform the refueling. It has the docking interface at front, so it can dock with the chase vehicle. And it has the capturing here for the robotic manipulator to grab on and pull us towards it. Next, we have the chase vehicle system. The chase vehicle system is supposed to hover and translate towards the target vehicle and support the robotic manipulator through its refueling. It does this by also having 2 visual tracking nodes for the visual tracking system to watch it, and it has a docking interface in which to connect to the target vehicle. It also has the robotic manipulator attached on top here. Its base plate fits right on top of us, and it performs its job by having the end effector, which is actually what grabs onto that ring and pulls us in. And then it has a refueling receptacle inside of the end effector, which will actually come out and perform the refueling mission. To give a visual of what I just talked about, the visual tracking system will communicate with both of these throughout the mission. The 2 docking ports will connect together, and this is where the refueling receptacle is for the robotic manipulator. Next, I would like to introduce Lee Morris to talk about the visual tracking system.
Thank you, Nina. As you said, my name is Lee Morris. I'm the team leader of the visual tracking system. Here we just see our design structure tree. You can see the visual tracking system is broken down into 3 subsystems: the controller, the communications, and the camera. Going on with the overall system description, you can see, as said before, the visual tracking system is positioned above the demonstration table and uses camera with object recognition of the colored nodes to determine the position and orientation of both the chase and target vehicles. It then transmits that vehicle position and orientation to the chase vehicle system. Here we have an overhead view. You can see that all the electronic components are just simply mounted to a baseboard, which is then secured to a mounting pole that will attach to the ceiling of the lab. Going at the system level requirements, we just have a single requirement, and that is that the visual tracking system shall be positioned at a height above the demonstration table greater than or equal to 2.5 meters. This came from considerations of a variety of wide-angle cameras that we were considering so that they could see the entirety of the demonstration platform. Now onto the controller subsystem requirements. We have 2 accuracy requirements, and that be that the controller subsystem can track the absolute position and orientation of both vehicles to an accuracy of plus or minus 10 millimeters and plus or minus 5 degrees. These values came from anticipated capabilities of the robotic manipulator. Next, it should be able to receive data from the visual tracking camera subsystem at a rate greater than or equal to 20 frames per second. We chose this design frequency based on the control frequency of the caster or the chase vehicle with an improved factor of safety for added performance. Next, it must be able to transmit data to the communication subsystem at a rate greater than or equal to 9600 bits per second. This comes from our control frequency as well as the size of the data it takes to represent our position and orientation. To validate these requirements, we have selected the Raspberry Pi Zero. As you can see, it has a serial port that is capable well beyond our desired baud rate. It has a camera serial interface that can receive images at 1080p and 30 frames per second. And it will be running a Python script of OpenCV computer vision library on a Linux-based operating system. At this moment, we are unable to validate our accuracy requirements as the system is rather complex and we don't have the capability to simulate what the accuracy will be. So that will have to be done with physical tests in the future. Moving on to our camera subsystem, the 2 requirements for the camera are that it be able to send image data at 20 frames per second, again that is our control frequency, and capture images of resolution greater than or equal to 720p. This 720p requirement came from an initial demonstration table size, approximately 360 centimeters on each edge, so we would need at least that resolution in order to get our desired position accuracy of plus or minus 10 millimeters. To validate these requirements, we have selected the Blue Robotics wide-angle camera. As you can see, it's capable of capturing 1080p at 30 frames per second, and it has that same camera serial interface as the Raspberry Pi Zero for compatibility. Lastly, we have the communication subsystem. The requirement for the communication subsystem are that it be able to transmit at a range greater than or equal to 4 meters, which is the height of the lab where we'll be performing our test, and that it should be able to transmit that data at a baud rate of 9600 bits per second, which I explained previously. To validate these requirements, we have selected the HC05 serial Bluetooth transceiver, and as you can see, it's capable of that desired serial communication well beyond our 9600 required baud rate, and it has a range of 9 meters. So thereby validating all of our requirements. Next, I would like to introduce Rachel Pope, who will be talking about our target vehicle system.
Thank you, Lee. Hello, everyone. My name is Rachel Pope, and I'm the team lead of the Target Vehicle System, also called POLIX. First, we have our design structure tree. I will be going over the system itself, its subsystems, and the components. First and foremost, our first and only objective is that it should remain stationary on the demonstration platform for the duration of the mission. Also, some other quick notes. It needs to be positioned 1.9 to 2.1 meters away from the chase vehicle system, also called caster. Also, it needs to dock with caster. It will receive an electrical current from the robotic manipulator, and then that will light our LED for visual confirmation that we have refueled. Going into our CAD a little bit more, we have our 2 tracking nodes on the top of the system. This will be for the visual tracking system to find our position and orientation. Next, we have our capture point. That is where the robotic manipulator will be able to grab onto the system and pull the 2 to dock. Next, we have our guidance cone. That will guide the robotic manipulator towards the refueling receptacle. The base is made out of 2 plywood plates, one of which will be hollowed out for our 25-pound plate. This will make the system much heavier, and I will go into detail on that later. Next, we have our docking interface. We have 4 mending plates that will attack the docking interface frame to the system itself. On the other side of the frame, we have a steel plate. The reason we chose steel is because we are using electromagnets on the chase vehicle. So we need something that is attracted to magnets as well as electrically conductive. Next, we have a refueling circuit, which is made up of a negative-positive-negative transistor, a 0.1 farad capacitor, a 100 ohm resistor, and lastly, an LED. On the bottom of the slide, you can see the circuit that we'll be using. Please take note that the battery will actually be located on the robotic manipulator. That will be providing our fuel once it has connected to the refueling receptacle, which will close our circuit. Moving on to our requirements, we only have one requirement, and that is for the geometric center of the target vehicle to stay within a radius of 210 millimeters. Some mitigations that we have are to make the target vehicle much heavier, which is why we have that 25-pound plate. Also, since the chase vehicle will be on air bearings, it will have a very low coefficient of friction, so when the 2 dock together, the only vehicle that should be moving is the chase. Moving on to our subsystems. First, our electrical, we require a 0.1 farad capacitor as well as a 100 ohm resistor. This is based off of Sparta Robotics' calculations. Moving on to the structure, we need a docking interface, a refueling receptacle, and our diameter needed to be between 300 millimeters and 350 millimeters. So we do have our docking interface as well as our refueling receptacle here in the middle. And we did decide on a diameter of 320 millimeters. This way we'll be able to hold all of the components that we need, as well as house that 25-pound plate. And then this will make it so that it's small enough so that the radius does not exceed the length of the robotic manipulator. And lastly, we have our components. The docking interface needs to be able to dock with the chase vehicle at a maximum range of 2 millimeters away. Moving on to the refueling receptacle component, it needs to accommodate a 3.7 volt electrical input from the robotic manipulator. This is based off of Sparta Robotics' calculations. Now I'll hand it off to Raul Gonzalez, who will go over the chase vehicle system.
Thank you, Rachel. Hello, everyone. My name is Raul Gonzalez, and I'm the Chase Vehicle System Team Lead. Before I begin, I would like to introduce the Chase Vehicle System team, which is formed by Yashika Khatri, Matthew Klockner, and Trupti Mahendrakar. The Chase Vehicle System, also known as CASTOR, is comprised of the following subsystems and components, all of which will be explained in this presentation today. I'll be talking about the Chase Vehicle System, the structure subsystem, and the manipulator mount component. To begin with, the objectives for the Chase Vehicle System were designed to simulate rendezvous mission, refueling, and docking mission in space. These objectives state that casters should hover over a demonstration platform, translate and rotate towards the target vehicle system, perform a refueling maneuver and docking maneuver with the aid of a robotic manipulator, and after this maneuver is completed, chase vehicle system should return to the starting position. Throughout the duration of the mission, the vehicle must remain stable. In this overview picture, it is possible to observe the docking interface and the robotic manipulator, which will help us to dock with our target vehicle, the air bearings, which will generate the lift for our vehicle, and the visual tracking nodes used by the visual tracking system that will allow us to calculate the position and orientation of the vehicle at all times. In this side view, we can observe the two compressed air feeds that go into our system. One compressed air feed goes to the air bearings, and the other compressed air feed goes to the translation mechanism, which allows our vehicle to translate and rotate. In this back view, it's possible to observe 3 air nozzles and 3 solenoids of a total of 8. These nozzles and solenoids are part of our translation mechanism, which allow us to, as I already said, to translate and rotate our vehicle. To meet our objectives, the following requirements were drafted. These requirements state that our chase vehicle should have a mass less than or equal to 65 kilograms, should be able to rotate 360 degrees about its yaw axis, and should have a pitch and roll angle in between 0.004 degrees and minus 0.004 degrees. These requirements come from the minimum height that the air bearings produce, that is 6 microns. Under these conditions, keeping the roll and pitch angles between these bounded conditions will guarantee that the chase vehicle system will not go under 6 microns, and thus reducing the risk of coming in contact with the demonstration platform. To validate these requirements, we've designed our system to have a total mass of 8 kilograms. This is well under the total maximum 65 kilogram requirement. Similarly, the 360 degrees rotation was validated with our translation mechanism, which will be further explained during this presentation. Finally, the roll and pitch maximum and minimum angles were validated using a computer simulation. These simulations show that under different states and mission phases, our vehicle pitch and roll angles remain under the bounded conditions. This simulation will also be further explained during this presentation. Now we'll continue to the structure subsystem and manipulator mount component. The objectives for our structure subsystem is that it should support the docking component, the docking interface component, and it should support the manipulator mount component. And finally, it should remain structurally sound during the duration of the mission. To meet these objectives, the following requirements were drafted. These requirements state that the structure should support 1 docking interface component, support 1 manipulator mount component, should be at least 300 millimeters, but at most 350 millimeters in diameter, and should be able to support a 3 kilogram robotic manipulator on top of the vehicle. To validate these requirements, we've designed a cuboid frame made out of ABS plastic with a top and bottom cover made out of aluminum with a 300 millimeter diameter. As you can see, this design validates our requirements and is able to hold a robotic manipulator and a docking interface. Finally, the structural requirements of the structure were validated using ANSYS software. These simulations show a slight deflection but not failure of the structure, and we'll be further looking into reducing this deflection by changing the material of the frame. To continue talking about the chase vehicle system components, I would like to introduce Yashika Katri to continue talking about the hovering mechanism component and translation mechanism components.
Thank you, Ro. Good afternoon, everyone. I'm Yashika. I'll be presenting the hovering and translation mechanism components, as you can see on the design structure tree. Starting with the air bearings. Air bearings use a very thin layer of pressurized air to hover over the surface. As Raul showed in the CAD model, there are 3 air bearings being used, placed in an equilateral triangle for stability. Currently, our objectives state that casters should be able to hover for the entire duration of the mission. The requirements state that the hovering should be at the minimum height of 3 microns and air bearings should be able to use a maximum pressure of 827 kilopascals, which is available at the lab where we'll be performing all the testing. The design metrics we considered can come from the air bearing manufacturing information. They state that larger air bearings operating at lower pressure increase stiffness and rigidity of a body. When we considered the number of air bearings to use, we came up with the fact that 3 air bearings imply easier alignment because 3 points define a plane. Aligning another one with it would be very difficult. Along with that, we wanted to consider the shape of the air bearings. Circular air bearings have uniform lift all around them, versus rectangular air bearings for which it varies with the side. The weight carrying capabilities were also important because we wanted to make sure that they can actually lift our systems together. To validate all the objectives, requirements, and design metrics, we went with 3 40mm new way air bearings, which have a minimum height of 6 microns, which is way over the 3 microns that you saw in the requirements. Along with that, they can function at an input pressure of 413 kilopascals, which is half of the 827 kilopascals, available in the requirements. Along with that, the max loading is 68 kilograms, which is way over the 11 kilograms where a caster and robotic manipulator together stand today. I'll now be going over the air filters. In the industry today, we have 3 types of air filters available: general purpose, coalescing, and a drying filter. The general purpose filter take out the bulk particle and reduce the particle size. The coalescing filter further reduce the particle size, and the drying filters take down the dew point. Currently, requirements state that air bearings should be able to function at a quality class 4 or better under ISO 8573.1, and the solenoids under translation mechanism component should be able to function at a quality class 7 or better. Based on these ISO requirements, we came up with the design metrics for air bearings to be able to function at a 15 micron particle size or less, and 3 degrees Celsius dew point or less. Along with that, the solenoid air supply should be at a 40 micron particle size or less, and there is no drying specification currently. To meet all these requirements and design metrics, we came up with the new way 2-stage coalescing air filter, which is a combination of the general purpose coalescing and the drying filter. It takes the particle size down to 0.1 microns to give you a relation that's the size of a smoke particle. And it takes the temperature, dew point temperature, down to negative 40 degrees Celsius, which is way under the 3 degrees required. Along with that, we went with the Festo air filters for the solenoid air supply, which takes the particle size down to 40 microns that was required by the solenoids we're using. There is no dryness specification. I'll now be going over the air distributors. As you can see from the diagram, air distributors take in one input and divide it into multiple outputs. The design metrics we considered for this was a 4mm nylon tubing that's compatible with our air bearings, 11 outputs that we need, 8 for the solenoids and nozzles, and 3 for the air bearings. Along with that, the 2 supplies that we have available at the Space Systems Lab, where we'll be doing all the testing, that can be set to different pressures. Based on all these, we came up with air distributors that are 2 of the 4-way distributors, and 1 of the 2-way distributors for the solenoid airflow, as you can see there, and 1 3-way distributors for the air bearings, as is shown there. I'll now be passing it on to Matthew Klockner for electrical controller and communication subsystems.
Thank you, Yashika. My name is Matthew Klockner, and I'll be going over the electrical, controller, and communication subsystems, as you can see here on this design tree. I'll start off by going over the electrical subsystem. The objectives of our electrical subsystem are that they should accommodate a battery as well as a 5-volt regulator. The requirements associated with these objectives include accommodating 1 battery with a nominal voltage of at least 11.2 volts, as well as a 1 5-volt regulator component for our microcontroller. In order to investigate these requirements, we designed a matrix, which included doing research into our microcontrollers, solenoids, and Bluetooth transceivers to find the shown voltages here. And Sparta Robotics provided us their required voltage for the robotic manipulator. Next, we found the voltage range and current draw from data sheets for our selected components. We calculated power from the power equation of power equals current times voltage. And we used all the values that Sparta Robotics provided us for their system. We also assumed a time of mission of 40 minutes. This includes our simulated time of mission times a factor of safety for, and then for validation, we are assuming that all of our systems are running at full power for the duration of the mission. As you can see here in this first table, we show the voltage required, the current draw, the power required, and the quantity of each of our components. And in the second table here, we show the max power, energy, current draw, and capacity required for the total 40-minute mission. As you can see here, we require a total of 3.85 ampere hours worth of capacity. This is slightly smaller than a normal laptop battery. In order to validate these requirements, we selected a rechargeable nickel metal hydride battery pack. This battery pack has a nominal voltage of 12 volts. It has a nominal capacity of 2.8 ampere hours. And so in order to meet our required 3.85 ampere hours, we'll be using 2 of these nickel metal hydride battery packs. Next, I'll be going over the microcontroller component. The microcontroller objectives include being able to control the propulsion subsystem, as well as being able to communicate with the robotic manipulator. The requirements associated with these objectives include being able to send and receive data to and from our Bluetooth transceiver at a rate of 9600 bits per second, as well as being able to actuate the solenoid driver at a frequency of 10 Hertz. It must also be able to communicate with the robotic manipulator at a required 115,200 bits per second. This is what Sparta Robotics gave us as their requirement. In order to investigate these requirements, we found that we needed 2 serial ports for our microcontroller, one to communicate with the robotic manipulator, and one to communicate with our communications module. We'll be using the same communications module as the visual tracking system, the HC05 Bluetooth transceiver. So our microcontroller must be compatible with this transceiver, and it must be capable of the required maximum bit rate. In order to validate these requirements, we selected the Arduino Mega 2560. This microcontroller is compatible with the selected Bluetooth module. It has 4 serial ports, which is in excess of the 2 serial ports that we require. It has a built-in voltage regulator to regulate the voltage from 12 volts to 5 volts, and it is capable of the required bit rate. Next, I'll be going over our solenoid driver component. The objectives of our solenoid driver are that it should regulate the power to the chase vehicle translation mechanism component, as well as being able to interface with the microcontroller component. The requirements associated with this is that it should regulate the 8 channels of power, and it should have a voltage rating greater than or equal to 12 volts. In order to validate these, we selected an 8-channel relay module. This module is compatible with the Arduino Mega 2560. It allows for 12 volts to pass through each relay, which satisfies the 12-volt requirement, and it has 8 channels satisfying the 8 different channels of power requirement. We'll also be using a 3V1 solenoid valve, which is capable of the required 10 cycles per second. Next, I'd like to hand it off to Tripti Mehankar for the translation mechanism and docking interface components.
Thank you, Matt. As Matt mentioned, I'm Tripti Mehankar, and I'll be talking about the translation mechanism and the docking interface of the chase vehicle system, which is also known as caster. This is the design structure tree. Moving on to the translation mechanism of the chase vehicle system. The translation mechanism of the chase vehicle system should enable the chase vehicle system, also known as caster, to move in the X and Y direction and also rotate about the yaw axis, which is basically the Z direction, which is perpendicular to the demonstration platform. To enable this, we will be using nylon tubing, as mentioned by Yashika earlier. So the coupling effect, which is the rotation, will be provided by the nozzles that will be arranged at 45-degree angle on either side of the chase vehicle here. And once it thrusts, it provides a rotation about this axis, which is the center point of the vehicle. The requirement of the translation mechanism is the translation of the chase vehicle system should be lesser than or equal to 0.2 meters per second,
and it should have a nozzle diameter of 4 millimeters and should operate at a pressure greater than 13 kilopascals, because at pressure less than 13 kilopascals, there is no thrust generated. The procedure that was used to validate our requirements was, initially we were assigned a demonstration platform of 12 by 12 foot in dimensions. We wanted the chase vehicle to travel for 60 seconds in the longest distance. So the longest distance of a rectangular platform is the hypotenuse. So using Newton's equation of motion, which relates velocity to displacement and time, we calculated the velocity to be 0.087 meters per second, which is way under 0.2 meters per second, and this validates our first requirement. The second requirement, which is the diameter of the nozzle, we do not have a converging or a diverging nozzle. It is basically the tube itself. And as Matt mentioned earlier, the solenoid's tubing diameter is 4 millimeters. So this meets our second requirement as well. Moving on to the third requirement, which is the operational pressure, we use the thrust equation to calculate the pressure difference that will correlate to the thrust. So this part of the pressure equation is called the kinetic thrust, and this is the pressure drop. So by setting one of these terms to 0, we calculated the thrust generated due to a certain amount of pressure. As we know, the exit area, which is the nozzle diameter, is constant. We use gas law, through which we calculated the density of the air, and this was calculated under atmospheric room temperature and pressure conditions of Prescott. This is the plot that was generated with the thrust equation. As you can see, 0.1 newtons of thrust, which is the thrust we need, is generated by having an operational pressure of approximately 14.6 psig, which is the gauge pressure, which is approximately 100 kilopascals, and this validates our third requirement. However, we were not able to calculate the pressure loss across the solenoid valves or the tubes, the bends in the tubes, as well as the air splitters. So we decided to calculate this experimentally by using 2 gauge pressure readers. We'll first be calculating the uncertainty in the gauge pressure reader by arranging the gauge pressure at the top and at the end of the tubing. And we'll use the same method to calculate the pressure drop across the nozzle bends as well as the solenoids and the air splitters. Moving on to the docking interface component of the chase vehicle system. This is the docking interface, and this is Castor, which is the chase vehicle. The docking interface component requirements is it shall be able to connect to target vehicle's docking interface component at a maximum range of 20 millimeters. This accounts for the thickness of the electrical strips, which I'll be talking about later. And it should also be able to complete an electrical signal, an electrical circuit, in order to send an electrical signal to the robotic manipulator that is on chase. So basically, there should be a gap of no greater than 0 millimeters between the two vehicles. That is our second requirement. The design matrix that were investigated to validate our requirements are the number of electromagnets that we would be using, the type of electromagnet, the electrical strips, and the release foam, which will be used for validation. The procedure that was used was, we initially investigated using 1 electromagnet. So if we use 1 electromagnet, it creates a point force. So basically it creates rotation about the docking interface of both the chase and the target vehicle. So we decided to go with 2 electromagnets, which will disable any rotation that will be created. And the type of electromagnet that we would be using would require 12-volt supply and a constant input of 0.08 amperes of current. This generates about 50 newtons of lift force. And we chose this because Castor itself uses a 12-volt battery supply. And using this electromagnet, we will not have to use a step-up or a step-down voltage regulator. Furthermore, electrical strips will be made out of steel because of its high electrical conductivity, and this is the same material that will be used on polys as well. And steel, for our electromagnets, a steel can be attracted by at a distance of 2.032 millimeters. So this validates our second requirement. And using release foam, we'll be ensuring that the placement of the electromagnets and the electrical strips will be in the same plane. So when both the vehicles dock, there will be complete contact between the electrical strips, electromagnets, as well as the docking interface of Pollux. This concludes validation of all of our requirements. Now, I'll be passing it over to Noor Rashid to talk about roll and pitch simulation for system of systems.
Thank you, Tripti. My name is Noor Rashid, and I will be discussing the system of system validation for roll and pitch simulation. To reiterate, this is our system of system design structure tree, and we have our system objectives. One of the objectives for Castor is the chase vehicle system should remain stable for the duration of the mission. Previously, we had thought that during the mission we will have roll and pitch perturbations. To ensure that we do not exceed the limits of the air bearings, we actually validated this objective using a simulation whose results will be shown in the next few slides. As Raul had previously stated, the chase vehicle system's roll and pitch angle shall be within the limits of plus or minus 0.004 degrees. And here we have the robotic manipulator fully extended onto the chase vehicle. As you can see, the whole robotic manipulator is 580 millimeters long. We will be using this as the extreme worst case scenario for the simulation, but the robotic manipulator itself actually has 6 degrees of freedom movement. We had used the extended version for the worst case scenario so we could get an accurate representation if needed. And here we have the perturbation simulation results. As you can see, these are all for the worst case scenario. The first row of the graphs is actually the roll and pitch simulation of a linear model of the lift from the air bearings above the demonstration platform. The limits, or the red lines that you see, are the air bearing limits or the air bearing tipping points. And this actually corresponds with our requirements of plus or minus 0.004 degrees. For the duration of the mission, which is 2400 seconds, we realized that the linear model is unstable and actually goes out of the bounds. We then spoke to the manufacturers of the air bearings at New Way and concluded that a polynomial model of the simulation is a better representation of the air bearing behavior. Therefore, the second row of graphs that you see is the quadratic model of the simulation, as the air bearings do not, operate on a linear scale, and as you can see, it's very close to zero. Therefore, validating our requirements, and also we can see that hopefully we will not be failing. And now I'll be passing it on to Seven Reinhardt for the flight simulation.
Thank you, Norm. I'm Seven Reinhardt. I'll be talking about the system validation and the flight simulation itself. First, to go over the requirements and validation of the system. To begin, we have to have one chase vehicle system, a target vehicle system, one visual tracking system, and one robotic manipulator system, which we have already previously defined and that you've seen throughout this presentation. The second requirement that we needed was that we needed a chase vehicle system and a target vehicle system to start at a distance that is greater than or equal to 1.9 meters apart and at a distance that is less than or equal to 2.1 meters apart from each other at mission commencement. We validated this by creating a full flight simulation with the two vehicle systems positioned at their maximum distance apart. Now I'll be going over the full flight simulation. The flight simulation simulates the velocity that the propulsion system will achieve, and a deadband controller that is used on the Castor vehicle system. It also has the equations of motion of the chase vehicle system in the X, Y, and yaw directions, and it has an emulated visual tracking system with predetermined coordinates. We put together an animation for you to show this full flight simulation. At the bottom left here, you have the chase vehicle system, and in the upper right you have a target vehicle system. It is important to point out that we are looking down on the demonstration platform from the view of the visual tracking system. To begin, Castor will go ahead and initializing its power. Yeah, there it goes. And you can see that the Castor system will then rotate itself about the yaw axis into its inertial frame. Then it'll go ahead and translate in the X and Y direction until it reaches its target vehicle system. It is important to point out that the robotic arm is folded up during this entire simulation, but in reality it will be extending. It'll do that right after it aligns itself with the target vehicle system, which it is doing now. So now that it has aligned, the robotic arm would go ahead and grab onto that capture point and pull itself in, and then the two plates will connect for docking. During this time, the robotic manipulator will release and it'll fuel the target vehicle system, then release, and then the two will dock or undock from each other. Then the caster vehicle system will then rotate along the yaw axis and put itself back into the inertial frame, and then it'll travel in the XY direction back into its starting position. I do want to say that this animation was completely put together using MATLAB, Simulink, and CATIA, and this entire simulation would take about 40 minutes. And now that the chase vehicle system has returned back to its original position, that is mission complete. And now I'll pass it over to Catherine Aya, and she'll go over the conclusions in programmatics.
Thank you, Seven. To conclude our preliminary design review today, I'll be starting with some conclusions in programmatics. There are several lessons that we learned during this design project, especially for such a large-scale interactive design project between two majors. First and foremost, we learned the value of simulation. Being able to have a full understanding of a system before it flies, such as those very small roll and pitch angles, or exactly how this vehicle will translate and locate the other vehicle, proved to be invaluable in our understanding of what needed to be achieved and how we would go about achieving it, and definitely fueled many of our design choices along the way. Team dynamic was also a really interesting thing that we learned, since not only are we a team of 10 people, but Sparta Robotics is another team of 7. So being able to work and communicate effectively and efficiently was a critical thing that we had to learn in order to make this project come to life. We also learned how to work with different kinds of mindsets throughout the project, between Astro and robotics and the different things that we've learned along the way. Last but not least, the importance of objective constraints and requirements cannot be overlooked. Having to be able to work to specific design metrics ensures mission success and allows us to understand exactly what we are doing as we are doing it throughout the design process. Here we have an hours breakdown of what the team worked throughout the semester, coming out to a total of 1,987 hours cumulatively between all of our members. We had a total budget of $1,600 for this project. We purchased 40 different parts. We will be purchasing 40 parts for this project, coming out to a total purchasing cost of $951. We did have 17 donated parts as well, including the air bearings that we will be using, as well as the demonstration platform, which is an industry-grade slab of granite that has a very precise flatness specification, courtesy of the College of Engineering and Dr. Jacopo Gentilini. This comes out to a total donated cost of $13,803, mostly going to that demonstration platform. It's a total equivalent expenditure of $14,754. So again, this project would not be possible without the assistance of the College of Engineering, and we are very grateful for that. At this time, we'd like to acknowledge all of the people who have helped us along the way during this project, especially our main points of contacts and professors, Dr. Julio Benavides, Dr. Jacopo Gentilini, and Dr. Patrick McElwain. At this time, I'd like to open the floor for questions, and thank you so much for attending our PDR today.
Well, I'm noticing a trend here. All three of these Astro presentations have been great.
Thank you.
Oh, sorry, 3 that I've watched. I'm sure there were more. But like I said earlier, I come from an airplane world, so it's a lot for me to take in.
That's true.
But I just have a couple of things. So early on, I know you showed the animation of your system. I know a lot of the robotics teams, they usually do some sort of kinematic animation or something like that using CATIA. I know you had a simulation later on. That would have been great to show at the beginning, just something along those lines that would have helped me follow along a lot better. Just back to another example of, tracing back to the big picture. I kind of got lost in the small details. So I'm a structures guy, so I was kind of on slide 40, or no, what does that say, 59. So I was kind of sad that you left out the analysis you're talking about. I think the reasoning was that the deflections were smaller, something like that. I just wanted to get hear from you guys why you didn't include that.
So we actually did include it in a backup slide. If I'm being honest, we did it a little bit late in the process, and we didn't want to interrupt the flow of our presentation, if that's the truthful answer. So Nora, if you could pull up the backup slides. We do have the ANSYS model here, and I'm going to pass it to Raul to discuss this piece of information.
Okay. So as you can see here, we can see the simulation that we run using ANSYS. This is applying a factor of safety of 1.5. Our requirements state that we should be able to carry a 3 kilogram robotic manipulator. This is around 5 kilograms. The simulation, as you can see, there's a deflection in the air bearing placement where we place the air bearings. So that's why I mentioned that we will be further looking into reducing this deflection by changing the material. Currently, this material was simulated using ABS plastic.
Okay. Yeah, just goes back to one of your requirements was must be structurally sound, and I didn't see any way to trace that besides something like this. So this is a key part of your story of traceability and compliance there.
So to continue on that, we had defined structurally sound as in one piece for the mission. So we did meet that. However, one thing we do want to run further simulation into is the air bearings are on ball sockets when they are in the model, which we were a little bit unsure of how to actually simulate that in the ANSYS model. So the deflection in reality might be slightly less, but we will be running further simulations to validate that.
Perfect. And just the last thing, your lessons learned slide. Once again, I like seeing these. And you know, you're absolutely right. I heard someone mention. I thought it was really cool. You said that the robotics team working with those. Someone said this requirement was given to us by the robotics team. So having an interdisciplinary flow of requirements, trying to figure out what each other needs, working with different disciplines. I think that's a really valuable experience. As you go into industry, you're going to find that you'll benefit greatly from this project. So great job, guys.
Thank you so much.
Great, yeah, it's a huge amount of work, but I'm sure you guys know that better than me. Question on the fuel transfer mechanization. So as far as fuel transfer, I guess with this model versus, I guess if this were to be done full scale or in maybe a less academic environment. So the way you guys were modeling fuel transfer was just making an electrical contact from chase to target?
Sort of. So to elaborate on that a little bit, the robotic manipulator is going to have a barrel plug in the middle of its effector here. I can't actually open these ones up, but they would fold backwards. So once it has grabbed and pulled this towards it, these grabbers would fold back and there would be a barrel plug that would be inserted directly into here and charge it much like you would a laptop with a barrel plug. So that'll actually provide a small amount of current to charge a capacitive circuit, just like charging a battery, which will light up an LED right here. And so that'll show us that the circuit has been refueled. We are also working on developing a series of serial communications so onboard the robotic manipulator, once that refuel is completed, the manipulator will know that and relay that back to the chase vehicle system and say, okay, it's time to undock now, we've completed what we wanted to do here.
Sure, okay, so when you're using the term fuel just for an energy transfer, you're not planning on having some kind of hydrocarbon or some kind of thing that way?
We had thought about that in the beginning, and Nora, if you want to pull up the backup slide of our original design matrix, it's towards the middle. We did look at a variety of things. We looked at water, we looked at oil, we looked at gasoline, all sorts of different fuels, but based on, sorry, keep going, please. Keep going, please. I know. I don't remember where it is, I'm really sorry. Oh, go back up one, please. So this is from our very preliminary design choice matrix, but we did look at battery replacement, battery charging, capacity charging, oil, water, compressed air, confetti even, and solid rocket motors. We looked at everything, which is represented here. And so based on the design choices, we had looked at cost, ease of implementational, functional result, and all that. We had narrowed it down to the confetti and the batteries, and we decided that batteries were going to be a smarter choice for the purpose of this project.
Sure, okay. Cool, yeah, and so then for next semester, are you planning to actually have that plug implemented, or is that still going to be kind of a notional thing?
That will
on
be
the
implemented.
target?
So this represents that breadboard that you see here.
Copy.
So we will be making that breadboard capacitive circuit, and then Sparta Robotics is developing that actual refueling system on board their manipulator. So the battery will sit in that base and have current that will go up through it and actually be able to run that in the actual
Okay,
mission.
That clears up so much. Thank you so much.
Thank you.
And then actually, I really like the lessons learned slide. Again, I think that was great. It occurs to me that the phrase "all models are wrong, some models are useful" comes up when you talk about the value of simulation. So I'm curious, as far as requirements exchange between your two teams, this is kind of going to a new topic. As far as requirements exchange between your two teams, how did you facilitate that, or how did you formalize your information exchanges?
So in the beginning of the project, the two projects were both created by each of our respective professors, Dr. Benavides and Dr. Gentilini, so they were kind of in line to begin with as far as what we'd be doing. But we did create a contract between the two teams at the beginning of the semester to say, okay, this is what we're developing and this is what you're developing. So for instance, early on we established, how do we want to do this refueling? Is it going to go through our docking ports, or is it going to go through the manipulator? What do we want to do? So we agreed to those things early on and then developed our requirements based on those initial discussion and decisions. So that drove our objectives, constraints, and requirements documents. And then we had weekly meetings where we referred back and forth with each other to say, okay, so where is this at and where are we at? And that's changed a lot. We need to go back and fix that because that doesn't match that anymore. So lots of just back and forth discussion and updating to that contract every so often, and attending each other's presentations to make sure that we all had the same big picture in mind. But some things, when we encountered, a certain issue that caused robotics to say, oh, okay, we're going to need to make this longer, so we're going to have to update our requirements. So yeah, a lot of the back and forth.
Okay. Yeah, I think, and you guys will find as you get out there, having email fights or VTC fights are super fun, but actually just going and meeting people face to face solves a million problems so much faster.
We've definitely learned
I
that.
highly recommend keep doing that, because especially as hypothetically the government tells you to spend less money on travel or justify why you can't do this via VTC or via phone call, there's an immense amount of value to specifically going to meet people and get with them to understand their point of view. So, great job.
Thank you so much.
Wow. Being here today, I'll have to say, has been a humbling experience because in many ways, the professionalism of all of your presentations has sometimes, I have to say, exceeded real design reviews that I've been to.
Thank you.
And I mean, just the amount of work the hours that you put into preparing this review are significant. I assume those are book kept on the hours that you...
That was 11 p.m. last night was when they were capped.
Yeah.
And we did practice several more hours today.
Well, it paid off. It's really well called, very impressive. And as the other two have mentioned, extra kudos for integrating with a separate team. I mean, that experience is, I echo, going to be so invaluable when you get out in the real world, although you guys already have a good idea of what that world is going to be like. Let's see, I only had 2 questions, and they were just to clarify my own understanding. The visual tracking vehicle, which is going to be suspended over the test plane, that just stays in a fixed location, right?
Yes, it stays fixed above the platform, and I can pass it over to Lee Morris to discuss a little bit more about how it functions, since it is a relatively complex system.
Yeah, and so basically in that way, it's just able to convey to the chase vehicle where it is relative to the target vehicle, what its altitude is, and so forth, and then the chase vehicle itself has the intelligence on board to act on that information and close it and make the rendezvous. So in other words, the visual targeting system is not providing any of that logic. It's just a kind of a passive viewing platform.
Correct, yeah, to maximize the amount of processes that we could do on the images themselves, we decided to have all of those computations to be done by the chase vehicle. So the visual tracking system's sole purpose is to find the position and orientations.
Yeah. And who's building the software to actually take those data from the visual tracking vehicle and provide the logic that fulfills the mission?
Right, that will be performed by our team. Currently, we're planning on using OpenCV, which is an open source computer vision library.
I think you mentioned that.
Basically, it has a wide variety of functions. So we apply a mask to the image to find the individual colors, find the centroids of those colors to get the position, and then with 2 positions per vehicle, we have a vector of the orientation.
Yeah. I mean, what you're doing is what we call, in my line of work, optical navigation. So that's complex work. So kudos for taking that on. And then the only other question I had was during Noor's presentation about the stability, the pitch and roll stability. You showed 2 families of plots. One that seemed to show, you know, a system that was not stable. And then I guess I missed something about what the difference was between that and what you call the quadratic.
So I'm actually, Noor presented this, but I will pass this to Matt, who did a lot of the work on this simulation. So you talk to that.
So the first set of plots you see up there are what we initially thought of as a baseline representation of how the air variants react when they move with relation to the ground. So when they go higher, there's going to be less lift generated, and when they go lower, there's going to be more.
Yeah, which would seem to indicate, you know, you have an unstable system that's going.
Yeah, it's essentially a spring system where it becomes unstable. After we called the engineers at New Way who manufactured the air bearings and talked to them, we learned that the linear model of that system is actually not correct, and they operate on a much more complex polynomial system. So we modeled it as a simple quadratic just to get a baseline understanding.
So it's just a matter of modeling the system in an appropriate way so that you could.
Yes, sir.
What we thought versus what reality was, and we were glad reality was better.
Yeah, and you learned something obviously from that. So great work.
Very nice job on this project. I'll make it easy on you. You guys have already answered pretty much all of my questions. So, I like what they said. Being able to communicate between 2 different teams is not something a lot of people get before they enter the real world. So definitely you should value the experience you've gotten from that.
Awesome job. I really have no question.
You've seen it the whole way along the way, so thank you for all your help.
You're realizing one of my dreams, so thank you.
Don't tell me this.
All right, we'd like to thank our panelists for coming in today. Thank you all for coming. We are spacecraft preliminary design. Next semester will be detailed design, and we look forward to seeing you then again. So, thank you.